All right, welcome back. So we'll still be talking about sources of magnetic field in chapter 12 today. So first, quick review. Last time we talked about the Biot-Savart law, which for every magnetic field that is actually produced by moving charges, which is current. Okay, so then if you look at one individual charge that is moving, the field produced by it is equal to mu naught over 4 pi, the charge, and v, the velocity, cross r unit vector divided by r squared. So r is pointing from the source to your point of interest. Mu naught is equal to 4 pi times 10 to the minus 7 in Tesla times meters over amps. So this is something similar to the when you calculate electric field. So this is the analog to the Coulomb's law in electric field, which E equals to 1 over 4 pi epsilon naught times kq in R head direction over R square. Okay, so similar to that. So if you look at a particular segment of a conductor, which that carries current, so then we are looking at a small portion of the current di. Okay, so so for I, so for that small portion of dl actually instead of di, so dl in that portion, so the current goes through that. You can actually calculate the what will be the charge excuse me, in a small segment, because I in the wire will be equal to dq over dt. Okay, so then if you look at dq will be I times dt, which if you multiply both sides by the equation by v, the velocity, then this is dl. Okay, so dt times v, velocity times time t will be dl. So I times dl will be the dq times v in the this small portion of the wire. Okay, so then plug this back into the Biot-Savart's law, you get the magnetic field produced by this small portion to be derivative of B, small portion, magnetic field of the small portion equal to mu naught over 4 pi I dl cross R over R square. Okay, so for the magnitude of that, it's going to be just the mu naught I dl sine theta over R square over 4 pi. And you integrate through the whole wire, that will give you the overall magnetic field at this point of interest. And we look at a few examples. And so basically we look at the thin straight wire, so infinity wire, and you would integrate then from one end of wire towards the other end of wire. Okay, so if this infinity, you do the infinity for the magnitude wise, the end, at the end you come to the conclusion when you do the integration, magnetic field at a point r away from the wire is equal to mu naught times I divided by 2 pi r. Okay. So magnetic force for the two parallel conductors or two wires in this case. Okay, so because for a single wire with current, it will produce magnetic field. Then the second wire with current will be influenced by that magnetic field produced by the first wire. So then there will be magnetic force on the second wire here. So the force per unit length, F divided by L, is equal to mu naught I1, I2 over 2 pi R square. Okay, so you can calculate B1 here, and then calculate force for the conducting wire, ILB in that case. Okay. We also look at the magnetic field produced by a current loop at the center of the loop. Okay, so in that case, again, you'll start with Biot-Savart's law for the magnitude in that case, and then integrations through the whole loop. At the center of that guy, it gives you a magnetic field of mu naught I divided by 2R. For a particular point on the axis that goes to the center of this loop, so it's equal to a different result. But again, you take a small portion of dl from the current carrying loop, and then integration. Due to symmetry, the magnetic field will be just having a z component, not the y component, okay, or x component because of symmetry. So at the end, B is equal to mu naught I over 2, R square over R square plus Z square, and then to the 3/2 power in the denominator. All right, so today we'll be looking at mainly Ampere's law. So this is something like Gauss's law in calculating electric field. Okay, so Biot-Savart's law is like Coulomb's law, and Ampere's law is like Gauss's law. So where Ampere's law relates the currents through a surface defined by a closed path to the magnetic field along the path. Okay, so specifically, you'll have a so this is what it says. Okay, so let's take a look at the test first. So it says the summation of the B parallel times delta L over all segments of closed path is equal to a constant times the current enclosed by the path. This relation is written symbolically as the following. So Ampere's law says summation of the B parallel delta L. Okay, so B parallel means parallel to the path, which is the tangential direction. Okay, so this circular path, and then D delta L, and then you take each of this delta L and then sum them up. Okay, will be equal to the constant will be mu naught times the current enclosed. Okay, so if in this case, then if you do that for the summation of the delta L times B parallel through this whole closed path will be equal to mu naught I1 plus I2 because there are two currents inside there. Okay, if you have I1 goes in one direction, I2 goes in the other direction, you'll be doing I1 minus I2. Okay, so if the currents are in the same direction, they will add up. If they are in parallel opposite direction, they will subtract each other. Okay, or if you take this portion, small portion, to be infinitesimally smaller, then you'll be doing dl instead of delta L. Okay, so then you are doing dl times b dot because you are taking the parallel to that dl component. So this is a dot product. So integrate through the whole circle closed path. Okay, so that's what it means. That equals to mu naught I enclosed. Okay, where again mu naught, this is the constant number, which is called the permeability of free space. Okay. All right. So let's take a look on the Ampere's law by just a single wire. Okay, so we have derived this expression with the Ampere's law. We can go a few slides backward. So in this case, okay, how about straight wire? The result, so you start from Biot-Savart's law, and then result is B equal to mu naught I over 2 pi R. Okay, R has been the distance from your point of interest to the wire. So in this case, let's see how we actually derive this from the Ampere's law. So Ampere's law says the summation of the B parallel times delta L, okay, equal to mu naught times I. Or we can say, in this case, we can do integration. We can do integration B dot dl, and that should equal to mu naught times I enclosed. Okay, so this over here, if you look at the PowerPoint slide, where R is the distance from the point of interest to the wire, okay, small r. So you can use your right hand rule. You'll see that so like that way, okay. So you'll see that the B field is always in the direction of the circular path, okay. So that means it's parallel to it, okay. So then, and then it should be a constant number. So this should be just B times, this should be constant, B times the 2 pi L, 2 pi R, okay. That equal to mu naught times I. All right. So then B will be equal to mu naught I over 2 pi R. Okay. So, and then this is the result we got also from Biot-Savart's law. So this is much easier. Okay. So this is similar to the Gauss's law, where you would have in this case, you are not choosing a closed surface, but you are choosing a closed path. Okay. So where your B will be constant along that path. Okay, you might have like a closed path that have different segments, like for example, a rectangular closed path. So then on each side, the B field will be a constant, but not necessarily equal to each other. Okay, or a square, or other types of shapes. Okay, so it doesn't matter. All right, but this will be an easier way to calculate the magnetic field, just like Gauss's law will be easier to calculate the electric field in some cases. Okay. All right, so let's go back to the PowerPoint slide. Looking at one example here. So this one says a hypothetical current flow in the z direction create the field, magnetic field, because it says B. Okay, so B for magnetic field is equal to, so B in bold as the vector is equal to C, a constant number, times X over Y squared in the I direction plus 1 over Y in the J direction. So it says so that's inside this rectangular region of the XY plane showing in the accompanying figure. Use Ampere's law to find the current through the rectangular. Okay, so what's the current through that rectangular? So let's take a look on here. So it tells out the B field. Okay, now it's a known. So, and in this case, so we can sketch the problem. Or you can also look at the figure in the PowerPoint slide. But here you have X. This is out of plane in that case, and then the paper is the YZ plane. Okay, YZ plane, X being perpendicular to the paper. All right. So here we have A1, A2, B1, B2. Okay, and then this is the area of interest. It tells us the B field. Okay. And it says the current goes through this in the Z direction. Okay, so the current will be in the Z direction. All right. So this is the area. We can pick this as our closed path, the side, okay, of this rectangular shape. So then we can integrate the closed path and then dl. That should be equal to mu naught times I. Okay. So we are looking for I. So we need to find this integration on the left-hand side of this closed path. Okay. So let's say we start at this point. You'll pick the direction of your path. Okay, and then we'll come back here. So then there are 4 segments. Okay, so on each side, the B field is slightly different from each other depending on the X and Y values. But this DL on this point, this will be dy, right? dy in the Y direction. Okay, and then this will be dx. This guy will be dy, and this guy will be dx. Okay, so there are four segments. So the first one, this is going to be integration of B field dot dy, and it's starting from B1 to B2. Okay, so we can say B1 to B2 lower and upper limits plus the B field times dx. Okay, so this is from A1 to A2, and then plus B now again times dy, but in this time it starts from B2 back to B1, so B2 back to B1. And the last part will be integration of B dot dx, okay, and from A2 to A1, A2 back to A1. That all equal to mu naught times I. Okay. So for the first part, B field, your B field is equal to actually C times X over Y squared times I plus 1 over Y times J. Okay, so that's your B field. So for the dot product, the first one dot doi, I dot doi, I in the y direction, dot y direction, right? So they are perpendicular to each other. So that the first one will be 0. So then you only have the second one dot that guy. Okay. So this will be then equal to 1 over y times dy. Okay, from b1 to b2 plus for the second one b dot dx. So then it will be this one having the right value. This one will be 0. This one dot that one will be 0. Okay, so then that will be x over y squared dx. This is from a1 to a2 plus similarly for this guy would only have the y component. So c over y, okay, dy, and then this is from b2 to b1 and plus again that guy. So this is going to be x or actually 1 second here. So in this case y is constant. Okay, so we can, because for the second part here, right, y is equal to b2, so this guy becomes b2 squared. And on the last one here, this is just b1 squared, okay, and dx, okay. And yeah, that should be c constant, I forgot about. So this, the first one will be c over y, the second one will be c times x over b2 squared, the third one will be c over y, and then the last one will be cx over b1 squared, okay, all equal to mu naught I. All right, so this one and this one, they are the same integration, but the limits are flipped, okay? So then one will be giving you the minus of the other one. So these two will cancel, okay? Then we only have this and this remain. They are not exactly the same. This is cx over b2 square, but this is cx over b1 square, okay? So this is integration of x. So then will be, the result will be x square over 2, okay? And then the constants remains. And this is from a1 to a2 plus for the second one, again, c over b1 square, x square over 2, and then a2 to a1, okay? So we'll have the same c over b2 square. I'm going to put 2 in here, and then a2 square minus a1 square, okay? And plus pretty much the same, but b2 becomes b1, and then a1 and a2 will flip. So then you'll have a1 square minus a2 square. So this will be like minus c over b1 square of a1 square minus a2 square, okay? That total equal to mu naught I, okay? So what you have at the end is c over 2 times a2 square minus a1 square, and then 1 over b2 square minus 1 over b1 square, okay, equal to mu naught I. So then I will be equal to everything divided by mu naught, okay? So then I will be equal to, bring mu naught to this side, okay? So that will be your I and end. All right, so let's go back to the slide. So this is the example in the textbook. So you can check the example 12.7 in the textbook, okay? So we'll also briefly go through this one. So you have a current carrying cylinder where the total current goes through is I naught, but it's homogeneous through the cross-sectional area. So it's asking you what will be the magnetic field actually somewhere inside the cylinder and as well as somewhere outside the cylinder. Okay. So this is similar to like charge distributions, and then you're looking for electric field inside the distribution and then also outside distribution. So the best way to do this is use Gauss's law. Or in the electric field case is to use Gauss's law. In this case, we'll be using Ampere's law. Okay. So we'll have two regions of interest, one inside the cylinder and then one outside the cylinder, okay? Where the radius of cylinders are. So then we'll be looking for B field when R is less than A, as well as B field when R is greater than A. All right. So for the scenario of R is less than A, let me call it the first part. Use Gauss's law, okay, where you can do like B dot dl equal to mu naught I enclosed. Okay, so in this case, we probably will be doing using current density J. We'll be using I divided by the area. Okay, so I divided by the area of cross-sectional area pi a square. That's the current density. All right, and then I enclosed, when the R is less than A inside the cylinder, will be equal to J times the area of interest. Again, let's call it A prime. So A prime will be less than A. Or we can call this as A0, then this guy will be just A instead of A prime. So A will be less than A0, okay? All right. So due to symmetric, if you have a closed path chosen, all right, where this is also concentric with the cylinder, so then this is R, so the magnitude of B field will be the same, okay? So then you'll be having like B field times integration of the whole path will be the 2 pi R equals to mu naught times J times R times the area A. So this will be mu naught, the J current density will be I naught over pi A square. The area will be pi R square. Okay, so you'll see cancellation, but let's just write this down first. So the cancellation will be this pi and this pi will cancel. Okay. There will be this R cancels the square. Okay, so then you move 2 pi to the other side. So your B field then becomes mu naught I naught over 2 pi times A square times R. Okay, you still have that R there. Okay, so this is when you are inside the cylinder. When you are outside the cylinder, okay, when R is greater or equal to that, again, B field dot dl equal to mu naught I enclosed. So I enclosed will be I total. This will be B times 2 pi R again, equals to mu naught now in this time, just I naught. Okay, so then divide both sides by 2 pi R, you get B equals to mu naught I naught over 2 pi R. Okay, so in the first scenario, B is proportional to R. That means B increases as R increases. In the second case, B is inversely proportional to R. So that means as R increases, the magnetic field decreases. Okay, so that's basically what we have in the PowerPoint slide. As it plotted here, so B increases linearly to R and then decrease inversely proportional to R. All right. So the application, so in this case, so this one says you have the current density in the long cylindrical wire showing the accompanying figure has as this is now it's not constant, it's not uniform current density, but it increases proportional to R. Okay, so YC is a constant. What's the current through the wire? what's the magnetic field? And for the inside the cylinder and outside cylinder, those two scenarios. Okay, so this one is similar to the previous one in the example, but it's actually now the current density is changing. It's not constant. We'll do the same procedure as we did for that one, but now the current is changing. All right. So let's see. I'm going to just draw the cross-sectional area here. Okay. And then this guy has a radius of r. It's asking us what will be the total current through. Okay, so total current I. All right. So we'll have to draw a small ring that has a radius of r. So this is r. And then this ring has an increment of dr, derivative of r. Okay, so dr there. Then this area of the ring is dA, small increment in the area. Okay, so dA equals to now 2 pi r dr. Okay, the circumference times the width. All right. So then the current di will be equal to J times dA. All right, and then we can integrate for the total current. So the total current I will be equal to integration of di, which is integration of J dA. Okay, and J is equal to C times R, dA is equal to 2 pi R dr. So we'll be integrating dr from 0 to the radius, and then that goes through the whole cross-sectional area. Okay, that will give you the I. Okay, so this is the first part. That's how you would calculate the total current. So this is 2 pi C will be constant. 2 pi C will go in front. And then you should have r squared because r times r dr from 0 to r. Okay, so the integration r squared becomes r to the q over 3. So then this would be 2 pi c r to the third over 3 from 0 to r. So this will give you 2 pi c r to the third over 3. Okay, so that's the total current. All right, now next. What's the magnetic field produced by the current for R less or equal to capital R? So that means inside the cylinder. Okay, so inside the cylinder, then you'll draw a closed path, a radius R. So let's take this as the closed path, radius R. Okay, so then again, you'll be doing the Ampere's law, B dot dl, that will be equal to mu naught I enclosed. Okay, I enclosed will not be the whole, the total current, but will be the current just enclosed by that portion. You can use the same as we did for that, but the integration limits goes from 0 to small r, not capital R. Okay, so you can calculate I enclosed first, which would be equal to the same thing, but from 0 to r, CR 2 pi r dr. Okay, so you can follow that, and then the result will be simply just 2 pi c small r to the q over 3. Okay, instead of capital R. So this will be the I enclosed. On the left hand side will be just B times then 2 pi R. Okay, because that's your enclosed. The closed path circumference should be 2 pi R. That equals to mu naught times that I enclosed. So 2 pi CR to the Q over 3. Okay. So then there's cancellation, 2 pi R, 2 pi, 3 will become 2. So your B field then will become just mu naught CR to the square over 3. Okay. That's your B field. Now outside the wire, greater than R. The same thing here, you'll be doing Ampere's law, mu naught I enclosed. So this enclosed will be the total current, which we have it in here. Okay, so then you'll have B again times 2 pi R equals to mu naught 2 pi C R capital R to the Q over 3. So this time 2 pi and 2 pi cancel, but small r does not cancel capital R because they are different. So your B field then equals to mu naught CR to the Q over 3R. Okay. So you would see that in this time, it actually increases, the B field increases as the B to the square, R to the square. So it goes up like that. And then on this part, when it reaches the capital R, it actually is inverse proportional to R, so that decrease down. Okay, so something like that. All right, let's show you the full solution for this guy. All right. So let's go back to the PowerPoint slide. Let's move on. Further application of Ampere's law. So we are looking at certain devices. So a solenoid, this is something like if you have a loop of current. So previously we know that for a loop, it produces magnetic field just as a bar magnet. Okay. Now if you want to increase the magnetic strength, then you actually put multiple loops together. So then the magnetic field produced will be amplified by the number of turns. Okay, if you have 2 turns, then it's twice of that. And 50 turns is 50 of that. Okay, so such a device, you have multiple loops stacking together. It's called a solenoid, or it's also called electromagnetic. Okay, so you can look at the magnetic field lines. So over here you have very dense magnetic field lines. So inside here you have very strong magnetic field. So you can actually the lines look like pretty much parallel to each other. So you can approximate that as a uniform field inside the solenoid here. Outside here, the lines are very few. Close to here is almost, you don't almost have any lines. So the magnetic field here will be very weak or 0. Okay. But let's take a look on the what will be the electric magnetic field inside the solenoid. Okay, so outside here is almost 0, so we then can have a rectangular shape of closed loop. Okay, so we'll take a cross sectional like a cut, a vertical cut of that. So cross sectional of that. So this will be the current. Okay, so on the top they go out of paper, at the bottom they go into the paper. So for the four sides of the closed path, this one will be having B times L, okay? And then this one will be B, but B is in this direction, perpendicular to this guy, so that will be keeping 0. Over here, B field is 0, so B times L will be 0. And then over here, again, B field and L are perpendicular to each other, so the result will be 0. So at the end, you get 0, 0, 0, okay? This side will be 0, this side will be 0, this side will be 0. Only on this side, 1, we will have B times L. And that should be equal to mu naught n I, or mu naught times I enclosed. I enclosed is n times of I. So then you have this how many turns here enclosed by this rectangular, that gives you that number n. So BL times mu naught n I, okay? So B field then will be equal to mu naught n over L times I, okay? So this is total number in the length of L divided by L, that gives you small n, which is the density, number density of the turns, okay, in a unit length. So the magnetic field by a solenoid is equal to that, okay? Either this expression or this expression. For toroid, which is kind of like a donut shape, okay? So instead of the like the cylindrical shape, this is donut shape. So it then produces uniform magnetic field inside the this donut shape, okay? Just outside of the donut, and the magnetic field will be zero, because if you look at, you can have a closed path, right? So inside here, then this closed path enclose this much of U times how many turns you have here times I. Outside here, because for this side, the current goes out of paper. For the other side here is going into the paper. So those two current cancel out, okay? And then also inside here in the center area, so if you have a circular closed path, it will not enclose any current. So then the B field inside there will be zero. Okay, outside will be zero as well. So you do B on this closed path times DL, which means B times 2 pi R. Okay, B times 2 pi R, that equals to the current enclosed. So then we'll be counting just this side, the inner side. Okay, so then it will be B times 2 pi R equals to mu naught times N times I again. So then B equal to mu naught Ni over 2 pi R. Okay, so this is for the toroid. All right, let's move on to the last section here. So what are some of the materials that has magnetism? Okay, so all magnetisms in materials. So if material has magnetism, that means the atoms inside the material actually has certain alignment. So then the electrons for each atoms, they have more electrons orbiting in one certain direction. Okay, or for the electrons, some of them may be caused by the spin of electrons. Okay, so if the electrons are all spin in the same direction, then they have the same, they cause this magnetic field by the spin of electrons. Okay, all right. Now, typically, electrons or atoms are in random orientations inside the material, so there's no net magnetic field. Okay, but some material has the tendency of atoms align up with each other, so and creating a net magnetic field. Those type of materials are called ferromagnetic. Okay, so ferromagnetic materials are like ions, cobalt, nickel, and gadolinium. Those types. So inside them, they have certain domains that have magnetic field, okay? And they more or less line up in one direction. So then the whole thing will have magnetic field, net magnetic field, okay? For other magnetic materials are called not ferromagnetic field, okay? Or let's just put it that way. So, but you can actually align the material domains inside the external magnetic field. So then they can line up due to the external magnetic field. Okay, so then they will line in one direction. As for ferromagnets, if you remove the external magnetic field, those alignment will still stay. Okay, so then that becomes permanent magnets. But it's just under a certain temperature of this temperature, 770 degrees. If you heat it up over 770 degrees, then magnetism will be lost, okay? So we know that our Earth's core is made of irons, the liquid irons, okay? So, and then geographically, sometimes you have an eruption of or kind of leak of those ions, and then when it reaches the sea bed, it will be actually frozen by the cold sea bed. Okay, so then that magnetism will be maintained when this is frozen, becomes molten salt rock. Okay, so then over the time, you'll actually study when that the Earth's magnetic field reversal happens. Okay, that will be information will be obtained by molten rocks. Okay, so other materials that are non-magnetic, ferromagnetic, are called paramagnetic. You can make the material domains inside them have certain orientation, so they will have alignment of magnetic field, magnetic domains. So then it will strengthen the magnetic field, external magnetic field. But this will be not permanent, because if you remove the outside magnetic field, then the material will lose that magnetism. Okay, it will become back to the original. But the amount of the magnetic field can be strengthened is called the susceptibility of the material. This sign looks like X. Okay, so magnetic field is then enhanced, right, by paramagnet. Finally, any materials, all materials together, they will have character called diamagnetism. That means if you have applied strong enough magnetic field to a materials, then it will actually become magnetic materials. Okay, so for example, you can put the frog inside a very strong magnetic field, and then it will actually be suspended in the air because of that magnetic field. Okay, so that's one of the example. We'll kind of stop here for today. Okay, and then we'll come back next time for the topic of induction. So I will see you guys later. Bye.